see. Okay, please help me welcome our speaker for the morning. Kenneth Farley is the W.M. Keck Foundation Professor of Geochemistry in the Division of Geological and Planetary Sciences at Caltech, and he is project scientist for NASA's Mars 2020 rover mission, a role he has had since the project's inception in 2013. Professor Farley received his Bachelor's of Science cum laude in chemistry from Yale University in 1986, and in 1991, he completed his PhD in Earth Sciences at the Scripps Institution of Oceanography, UC San Diego. He has been a member of the Caltech faculty since 1993 and is an elected member of the National Academy of Sciences and of the American Academy of Arts and Sciences. Professor Farley's research centers around the geochemistry of noble gases and on the development and application of geochemistry techniques to a wide range of terrestrial and solar system questions. His specific areas of interest include the geochronology of the Earth and of Mars. Ken Farley, welcome to the Greenway Talks online at Palomar. Thank you for taking time to be with us this morning. We'll take questions at the end, and you can also type questions into the chat. And for now, I'll ask everyone to turn off their microphones. And with that, excuse me, with that, Professor Farley, please.
Great, thank you. Thank you very much. It's a pleasure to be here. I don't think I can arrange this so that I can see the chat. So if somebody has a burning.
Yeah, we'll monitor the chat.
Okay, all right. If I need to answer, I'm happy to answer questions in the middle of the talk if that's important, or we can wait to the end. And you can see my screen, right?
Yes.
Okay, great. Yeah, I am a project scientist for the Mars 2020 mission. And that has been a really interesting experience. And I'll try to tell you a little bit about my personal, what this has been like to start out when this mission was just on paper. I spent a lot of time up at JPL working with first a handful of engineers, trying to explain to them what science needed for this mission. So I was the token scientist on the team. And then to watch it blossom into an enormous project with literally thousands of people working on it. And then now, after we landed on Mars, just shy of a year ago, on February 20th of last year, now I lead the science team, and meaning I have something like 500 scientists working on this, and we all have to work together and come up with a plan. And I'll tell you a little bit about how that whole operation works. We have been on Mars for 329 Martian days as of today. And I want to start off by telling you a little bit about the thing which most people know about. We successfully landed on Mars. Then I'm going to tell you about what the purpose of the mission is. And then I'm going to show you some early results. So starting with entry, descent, and landing, I suspect you all are generally familiar with how you land on Mars, but the big challenge is that Mars has an atmosphere, and you have to deal with that atmosphere. You have to aerobrake through the atmosphere, but the atmospheric density is not high enough that you can use a parachute all the way to the ground. If you stayed on a parachute all the way to the ground, the terminal velocity is so high that you would not land successfully, which leads to a very elaborate landing system. And I won't go through all of it, but I'll just show you some of the highlights. And I'll start with this orbital image of our landing site. I'm going to talk a lot about this landing site, but let me just point out some of the key features. This area here is a delta that was produced when a river flowed into a lake in this crater. And very conveniently, this crater is almost exactly 1 kilometer across. These cliffs here at the front are about 40 meters high. And our central target, for reasons that I will describe, was the delta. We wished to explore the delta. And the engineers, when they developed the landing system, had a technique that, first of all, could get us to a landing ellipse that was about 5 kilometers across. So I'm roughly showing you where that landing ellipse was. That's not good enough because within that landing ellipse, there are things like these cliffs that you cannot land on. So we had an additional capability that allowed us to deflect away from hazards if we are going to land on them. And what I'm going to show you is the video of how the spacecraft wound up where it did. Through a lot of modeling before we arrived, we had come to the conclusion that there was about an 80% chance that we would land in this very smooth area here, which we called the landing strip, which would have been fabulous because it was right in front of our main target. We figured we would wake up on our first day on Mars and look at these cliffs. That's not where we landed. We landed over here. And so I'm going to roll the video that that was taken, as I mentioned when we were discussing a few minutes ago. The engineers put a bunch of cameras on different parts of the spacecraft that were operating during entry, descent, and landing, just to see if it could be done. It has no scientific purpose, no engineering purpose. It's just, hey, can you do this? And it's pretty spectacular. So what you're going to see when this video starts is you will see the cliffs of the delta. You will see this crater called Hahuza. You will see that kind of looks like we're going to land in the landing strip. And then the divert maneuver kicks in because instead of actually landing in the landing strip, we were going to land in this feature we call Seta, which is this, I hope you can see this. It's kind of a mitten-shaped feature where you see these corrugations, these ridges. And as you will see in the video, it's absolutely filled with sand dunes. Do not land there because you cannot drive out. So it looked like we were going to land right around here. And it made a split-second decision to land us here, which is very interesting. As I will talk about, we cannot drive through this area. And to get to where we thought the most interesting thing would be is about a 4-month drive. So we landed in a place we didn't expect to. So let me just roll this because it's pretty cool. All right, so you're going to see here on the bottom. This is a much longer video that you can find on our website. But basically, the spacecraft is doing the interplanetary transit inside this shell that you see here. It's basically an aeroshell. The rover is all compressed inside there, and the rover is attached to a set of retro rockets. First thing that happens when you hit the atmosphere is you aerobrake. And that's actually controlled flight steering us to the landing site. So this is not just passive, it's actually steering. And once the spacecraft is aerobraked enough, we drop the aeroshell, the front piece, deploy the parachute. We descend on the parachute for a while, but as I told you, that's not good enough. And so in a move that seems a bit crazy, the rover attached to the retro rockets literally drops away from the parachute and takes some images to decide where to land for the reasons that I just said, and then navigates itself there. So this video starts right when we drop out of the back shell and the parachute. So this is the delta. This is rotated from the orientation before. Here's the Hahuza crater. We would have landed somewhere around here. And now we're swinging way over here, but we can't land here either. I'm going to show you some pictures of this area from the ground. So this is about 2 kilometers elevation when it started. The spacecraft navigated itself to a very narrow, about 50-meter wide zone, which was relatively flat. In just a second, you'll see the retro rockets kicking up the dust as we get close. And now we're going to cut to the actual cameras looking at other parts of the spacecraft. So that was looking down. And now we're doing the thing called sky crane, where we winch the rover to the ground And as soon as the wheels touch the ground, there's a bunch of pyrotechnic bolts that cut the bridle, and then the retro rockets fly away. And many people wonder, why does it need to be so complicated? Well, I've told you the first part of why it needed to be complicated, and that is you've got to deal with first aerobraking in the atmosphere. So you have to have a heat shield and all of that. You have to have a parachute to slow down substantially. But then you need to use the retro rocket stage to slow down enough. But the part that people puzzle over is, why do we need to do this thing called sky crane, where we winch the rover down to the ground? And this was very enlightening to me. I'm not an engineer, but I came to understand that engineers don't like anything that is not very deterministic. And one of the things that is not deterministic is if you allow everything to crash to the ground together, or even lower itself to the ground, you worry about everything being tangled up. There's lots and lots of parts that came down during entry, descent, and landing. And the engineers adopted the very clean solution: make sure the rover is just sitting by itself on the ground, free of everything. And so that's the basic design principle. So we landed in this area here, which we call the Octavia Butler Landing. This is the area called Seta. You see it's filled with sand dunes. These sand dunes are 1 to 2 meters high. We cannot drive through this area. And this area here, you can see some impact craters. I'll show you that it is way too bouldery to drive across. And so we landed on this very narrow strip, which turns out to be a fundamental geologic contact on the crater floor. So although at first we were kind of disappointed that we didn't land where we expected to, we actually discovered some really interesting things because of where we landed. And this is an image from the Mars Reconnaissance Orbiter of the rover sitting by itself on the ground. You don't see any of the entry, descent, and landing components. They all flew off somewhere else. And this kind of butterfly pattern that you see is where the retro rockets blew the dust out of the way. So we landed successfully. And of course, that was an enormous, exciting day. And this was just shy of a year ago. And I will just say that it was kind of miraculous that we made it because we had to get the spacecraft completed in the first 3 or 4 months of the pandemic, when the world was shutting down. And there was a lot of work to be done. And you can only launch to Mars about every 26 months. So we had a 3-week period. We had to be at the launch pad. And it was amazing to see the team pull together and have all these workarounds, because we started having challenges of sourcing even simple things like isopropyl alcohol. So we made it to the launch pad. We did the cruise and we successfully landed, and it was all done remotely. There's a very small team that meets at JPL, but we have been operating this mission remotely. And let me tell you, it is a weird experience to be working with hundreds of scientists and engineers every week who we have never met. We are all doing it remotely. And it's an interesting challenge, but so far so good. Okay, so let me tell you about the rover and the mission. The Perseverance rover is largely a rebuild of the Curiosity rover, because that was a very successful design. We have replaced some of the science instruments, all of the science instruments on the rover to meet our specific goals. And those goals are, first and foremost, seek evidence of ancient Martian life. And so I'll tell you about the key word in here, ancient, and why that's in there and what it means. The big goal, the thing that is the metric against we are constantly checking our progress, prepare samples for return to Earth. The ability to use the full array of analytical capabilities on Earth on carefully selected samples from Mars is going to be really important to answer questions that you just can't answer with instruments that can be flown. And as you heard about in my introduction, I work on geochronology. If you came to my lab at Caltech, you would see that I have instruments that literally weigh a ton. there's a big magnet that you need if you want to do isotopic separations, which is the way you do geochronology. You need an enormous magnet. There's no way those are ever going to fly, at least not in our lifetimes. So you kind of bring samples back, and I'll tell you a little bit more about that. And a third goal is it's a very NASA specific sort of objective. They could just call it enable the future, which means fly new technologies that could be useful for future space exploration. We have two elements of that I will mention. The first is we have an instrument on board the rover which demonstrates the capability of ingesting atmospheric CO2 from the Martian atmosphere and converting it with electricity into oxygen, which would be useful as a part of the propellant for human exploration. You need an enormous amount of oxygen to have a rocket that can get you back off of the surface of Mars, and you'd be much better off if you could make it in place. We've demonstrated that capability. It works very well. The other feature that's part of this enable the future is the Mars helicopter, and I'll show you some video of that in a little bit. Now I want to just digress for a minute and talk about life. We know that the present surface of Mars is inhospitable to all life as we know it. There is nowhere on the surface of Mars where life as we know it could exist. It's too cold, it's too dry, and there's too much radiation. Without a magnetic field and with a very thin atmosphere, the surface is bathed with really lethal levels of both ultraviolet light and galactic cosmic rays. So there is nothing that can live on the surface. Now, what's interesting, though, is that the missions that have gone to Mars over the decades have come up with one consistent observation that is very hard to understand, but is unambiguous. Mars climate used to be very different. So I start with this image from the Curiosity mission, which is exploring a different crater called Gale Crater. And you look at this image and you should be thinking, well, that doesn't look like a very hospitable place. Looks like the most arid desert you could imagine, and it is. But the features that Curiosity discovered are apparent to anybody with geologic training. These are sediments, and these sediments were deposited in a lake. So this crater once hosted a very large lake, and that was about 3.5 billion years ago. So there was this enormous climate change that happened on Mars about 3.5 billion years ago, and I can return to this if you're interested, but it's probably somewhere more like 3.5 plus or minus 500 million years. And the age of the solar system is only 4.5 billion years. So if you have an uncertainty range that's 1 billion years, you haven't really narrowed it down all that much. But early in its history, Mars desiccated. So if you're going to look for life, don't look in the present surface because you are very unlikely to be successful, at least if you're looking for life as we know it. And if you're not looking for life as we know it, it's going to be hard to do because you don't know how to look for it. So instead, look at the geologic record. And so that is the basic strategy, recognizing that 3.6 billion years ago, Mars might have looked, unlike today, it might have looked something like Earth. Lakes and rivers for sure. There's a hypothesis that is always debated, and I'm not sure that we are getting any closer to the answer just yet, but there might have been an ocean in the northern lowlands of Mars. So Mars might have looked not that much different than Earth at this time period, 3.5, 3.6 billion years ago. So the important question is, what should we be looking for in life that might have existed only 1 billion years after the formation of the solar system? And all we can do is use Earth as the example of one. So we look at Earth's geologic record, and indeed about the oldest rocks that you can find that have not been completely obliterated by modification after they formed are just about from this age. They are just about 3.5 and 3.6 billion years ago. And what you find in them, those rocks which are inhabitable environments, so I'm not talking about an igneous rock, one that crystallized from a magma, I'm talking about ones that were deposited in water, you find evidence of life. So within 1 billion years after the formation of our planet and all the planets, the Earth had been colonized. So whatever led to the origin of life, it had happened, and that life had proliferated. And this is an example of the oldest undisputed evidence of life on Earth. This is a feature called a stromatolite. It occurs in a very special place in Western Australia where rocks of this age are preserved. So most of the rocks of this time period have been destroyed. But in this area in Western Australia, you see this feature, this kind of bulbous structure. And this is called a stromatolite. It is produced when microbes that live on the bottom of a lake or a shallow sea essentially glue the surface sediment together. And then it winds up getting distorted in this characteristic bulbous pattern. Interestingly, we know that that's what this is because these things still live in some places. This is a living stromatolite in a lagoon also coincidentally in Western Australia. So we know that these things are evidence of life. So this is the kind of thing that we should be looking for using our example of one. We should not be looking for dinosaur bones or fish fossils. We should be looking for simple evidence of microbial life. And that makes it a lot harder in one sense because, you know, these are pretty subtle features. On the other hand, this is what we have available to us. Well, where would you go to look for that? Well, on Earth, those stromatolites exist in shallow lakes and seas. And our landing site, which is shown here in perspective view in Jezero Crater, is a very similar feature. It was a lake, and that lake was at least 100 meters deep and about 45 kilometers across. And it is of the same age as that stromatolite that I just showed you. So when thinking about looking for life beyond Earth, you always, you know, at least I always ask myself, well, how plausible is this? And in this particular case, we have an environment that's the same to first order from the same time period that life existed on Earth. In fact, this is the most habitable environment that we know about anywhere beyond Earth. And we are going to look for evidence of life in it, both with the rover and with samples that come back to Earth. And it will be important to know either way. If we find nothing, that will tell us something. So this is an important thing to keep in mind, that if you think that life is ubiquitous and you go to a place that life would have been able to thrive and you don't find it there, you have learned something. So this is the landing site. You can see this river flowing through about 1 kilometer high rim of Jezero Crater, 45 kilometer diameter crater. And this lake actually has an outflow channel. And that's pretty interesting because that allows you to estimate how deep it was. This was not like, you know, Death Valley, like the little dried up lake that you see in the bottom of Death Valley when you have intense rains. This was called an open system lake. River flows in, fills up the crater, river flows out. And it made this big delta. So this is an artist's conception of what this might have looked like. And I would just point out that a lake that is 100 meters deep and 45 kilometers in diameter, even by terrestrial standards, that's a big lake. You know, that's a Lake Tahoe, bigger than Lake Tahoe. So this would have been a big feature. Okay. I want to say a few words about the delta. So in this image, this is a delta, and it is produced when the sediment that is coming down this river hits the slack water of the lake. And this is familiar. So this is an image of a delta somewhere in Alaska. And what I'm going to show you is some of the details of the Jezero Delta that look very familiar. So the basic idea is this sediment is being transported by the water, and then you get these distributary channels that deposit the sediment out in the slack water. And I like this image because all these colors are various kinds of organisms living in the mud. That it motivates the idea that a delta is nice, not only because it indicates that you had a lake, but it is a habitable environment. And even better than that, it is self-preserving, so that microbes that are growing here are destined to be buried by more sediment that's coming down and in a relatively peaceful environment. So if you are looking for evidence of life, you don't want to go to a place like a rushing river in the mountains where the rocks kind of beat everything up. You want to go to a place that is deposited relatively quiescently, and that is exactly what a delta is. So this is why we went to Jezero Crater, because we have evidence of a delta. Okay, so I'm going to tell you more about that, but first I'm just going to show a little clip of the Ingenuity helicopter. So now I'm transitioning to talking about what we did on Mars now that we're there. One of the first things we did is test fly the Ingenuity helicopter. The challenge of a helicopter on Mars is that the atmospheric density is about 1% of the Earth's atmospheric density at sea level. So you can't do it with a little, hobby shop drone. This helicopter has blades that are about 1 meter across. They're a pair of counter-rotating blades. And as part of the technology demonstration, we did 6 test flights, and the helicopter performed flawlessly. It is remarkable how well this helicopter works. And you may not even be able to see what it's doing here, but it's basically hovering. This is its first test flight. Simply get up off the ground and hover. We proceeded then to do longer and longer flights. And the way a technology demonstration works is at the end of the agreed upon set of objectives being met, that the helicopter is done. It doesn't need to do anything. It was not designed to be a science instrument. But because the helicopter works so well, we have now repurposed it to be a science instrument. It flies out ahead of us and surveys the landscape for us. This is really important, both to see rocks that we cannot see, to see geologic features that we can't see from the ground because we're too low, and also to chart routes, to do reconnaissance for driving. So that's the way we continue to use the helicopter long after its initially expected life. So that's pretty neat that worked out so well. I want to show you a little bit of the science results. I'm going to start by showing you images of 2 features from the delta. So this we call the delta front, these 40-meter high cliffs. This little butte out here we call Kodiak. It is an erosional remnant, which tells us that the delta used to extend farther and has eroded back. This is very familiar. If you drive around in the southwestern United States, you see buttes produced in exactly the same way. They're just little erosional remnants of an original geologic layer. So I'm going to show you images from there. Then I'm going to show you the drive that we did around this area called Seta. I'm going to show you some of the results from there. So the first results that we got of this feature called Kodiak. So this is the butte called Kodiak. This is absolutely stunning. If you showed this image to anybody that has taken even an introductory level class in geology, they will recognize what this is. It has this very characteristic set of dipping layers. This is basically where the river was flowing out into the lake, and then the sediment, so just like this down here, imagine what happens here. Take this thing and tip it up in cross section, take the picture and imagine that you're looking at it in cross section. The sediment is basically pouring down a steep slope on the front of the delta. And these features that you see here were deposited at that stage. And then the delta migrates, it gets bigger and bigger and extends farther and farther out into the lake. And it gets capped by what are largely river sediments. So this is telling us exactly where the lake level was. So this is a really nice demonstration that this is in fact a delta produced exactly the way we thought it was. And we also know from this that the lake at this time was at a fairly stable level and the delta was growing. So that tells us a lot about the history of the lake. What you see in the foreground is that area called Seta with the sand dunes and the boulders. That's the area we cannot drive across. Even though we want to get over to the delta, we can't traverse this interesting terrain in the foreground. Well, that's what we saw in one part of the delta. But then when we looked elsewhere on the delta front, we saw things very different. So what you're looking at here is part of the 40-meter high cliffs. And this feature that you see here, which is about 100 meters across, and maybe 10 meters high. This is what it looks like when one of those distributary channels is cut in cross section. And you see, again, you see these all the time on Earth. This is a river channel preserved. But what's really interesting about this river channel is it is filled with boulders. So remember, we are way out in the middle of this flat crater, yet there are boulders. This particular one is 1.5 meters across, and there are others of a similar size. You do not transport a 1.5 meter diameter boulder by a little river like this. You just don't have enough energy. So what this is telling us is sometime after the deposition of the lower part of the delta, maybe in an environment that looked like this, there were big floods that came ripping across the top of the delta. It might have looked something like this here, capable of transporting these boulders. So this is telling us something about this transition, presumably about the transition that Mars went through from a period when there were stable lakes and rivers, maybe to its essentially the end of that period. Maybe there were flash floods at that end stage. We are going to explore this area probably sometime either late this year. This is still quite a ways away from us, so we're just doing what we call remote imaging now. We're going to actually drive up to that. I'm actually pretty excited about this from my own scientific interests, because these big boulders, and interestingly, we now recognize that there are similar boulders up here that were probably deposited in the same way. You ask yourself, where did these come from? Well, they must have come from a long way away, much farther away than the rover will ever drive. And so each one of these is a sample of a landscape that we can't see. And this is a classic thing that geologists do when they arrive in a new place. They'll go to a river and they'll look at the cobbles and boulders and rocks in the river to learn about what's upstream. So this is really nice. Nature has brought us the rocks to study. We don't have to go to them. So that was an interesting, very early discovery. We saw that within the first dozen sols of the mission. There's something interesting going on there. So after we had the rover all checked out, it took almost 100 days of testing out the various systems to make sure that everything was in working order. We began a drive. And I will just say that the reason we did this drive is we wanted to investigate what turns out to be this fundamentally different geologic features, the area we called Seta, and this area here we now call Maz. So I'll just show you some of what we found along this traverse. This is about 2.4 kilometers. We are still here at this blue dot, and I'm going to show you something interesting. We have an anomaly on the rover, and I will tell you about that, but we have not been able to drive. Something not good happened on December 23rd, and we've basically been stuck trying to fix it since then. That's just part of the deal. So we did this drive, and we will, as soon as we get this anomaly fixed, we will drive back and head all the way around Seta over to the delta. But let me show you what we found on this traverse. This is the area where we landed, and it's looking off to the east. And this is the area that I mentioned is filled with boulders that we cannot drive across. We were all very surprised how rough this terrain is. And in some ways, it controlled what we decided to do. So that's this area here. And we immediately decided, oh yeah, we're not driving through that. The rover cannot drive across that. It can drive through this kind of terrain where these boulders are maybe 20 centimeters high. We can drive over a 20 or 30 centimeter high boulder, but we can't go across this. So right where we landed, you see these low rocks, which we call either paver stones or whalebacks. These are, they're always right at ground level. Everywhere you look, and all along the traverse, the several kilometer long traverse, you see rocks that are right at ground level like this with just a little bit of sand on it. That's not a coincidence. These rocks are right at ground level because they have been planed off by wind abrasion, where wind picks up sand grains and erodes right down to the surface, right down to the surface of the planet. And we can see that this is probably not of high enough resolution, but you can see these lines here. These are features called ventifacts, and they are seen on Earth in places where you have very strong winds that pick up sand and polish rocks. So this motivates the idea that this landscape has been sitting here probably for billions of years. This is a very non-terrestrial sort of thing. On Earth, you do not have any landscapes that date back to that long. So this landscape has just been sitting here getting sandblasted for billions of years. It's something that's important to think about. Unfortunately, when rocks get exposed like this, they get covered with dust, and we can't actually see what's inside them. And we struggled for a long time trying to understand, are these rocks sediments deposited on the bottom of the lake? That's at least my going in hypothesis they would be, or are they something else? We really couldn't tell. If you look at these rocks, you don't see layering. Like I showed you at Gale Crater, where I said that's evidence that there was deposit in a lake. You don't see such layering in these rocks, which was puzzling to us. Well, ultimately, we got one of our new capabilities online. This was maybe around Sol 130, 140. We developed the capability to abrade the rocks. So we actually use a rotary percussive drill, and we grind a 5 centimeter wide, 1 centimeter deep hole in a rock. So we started with a rock that looked like this. We reached the arm out and we abraded this hole. And then when we looked at it, this was definitely, oh my gosh, really? This is not at all what we expected to see. And for many of us, just looking at this rock immediately brings to mind, wow, this looks like a granite. And if you have a granite countertop at home, I hope you can see the similarity. It's made of, minerals of different color. This is not, in fact, a granite. Has a chemical composition that's different from granite, but like granite, it indicates relatively slow cooling of an igneous rock. And we can see that because crystals are actually grown together here. So this is a surprising result. This is not a sediment deposited on the bottom of a lake. This is an igneous rock, and one that cooled slowly enough that it grew big crystals. That usually means it's well below the surface of the planet. So this was definitely a surprise. And the other surprise is if your eye is telling you this rock looks rusty, exactly. This rock has experienced interaction with water to do a lot of damage to the minerals that are here. This reddish material is probably iron oxide. And it also has these big holes in it and cracks in it. This rock has interacted with water in multiple ways. And if you look at these bright white patches, they are something else. I'll get to that in a second. So we have the ability to actually know what those minerals are. We have a technique called X-ray fluorescence that allows us to make maps. This is a new technology for Mars. The minerals of this rock, the dark minerals and the light minerals, correspond to igneous minerals that you would get in a crystallizing magma, including plagioclase and pyroxene. It's very familiar. This is an unsurprising composition. Once you accept that it is an igneous rock, this is exactly what you'd expect that igneous rock to be composed of, as well as this iron oxide that looks like alteration. And then the bright white patches. So here's a zoom in image of the bright white patches. We've been able to establish that these are salts. And in particular, they are sulfate salts and perchlorate salts. And these are almost certainly telling us that water dried down inside this rock. So picture a cracks in this rock that had salty water in it, and that water evaporated and left salts. And if you're familiar with the substance called caliche that you see out in the desert, we think this is something very similar to caliche. So this rock is an igneous rock that has been altered by water. That's pretty cool. That's I'll tell you why I say that, but that was a really interesting result. Now I want to talk about the sample return and how we actually have pursued that. So the Perseverance rover has on board 42 sample tubes that look like this. This is a core that we hope to collect and have now collected. It's about the size and shape of a piece of chalkboard chalk, just to get a scale on it. Each sample gets cored directly into its own sample tube, and then that tube gets sealed. So the idea is we collect those and we by a means I will describe at the end, get them off to a future mission, which brings them home. So we use this rotary percussive drill mounted on the arm, and I have a little piece of animation that shows how this is going to work. So the rover here has decided, well, we have decided that we want to collect this rock. The tubes are located inside in a structure you're going to see it's very complicated. Our engineers have said this is the most complex piece of hardware which has ever been flown for a space mission. On the arm is a rotary percussive drill, and right now it already has a sample tube in it. So we reach out, we take this down to the surface, we use a rotary percussive drill to drill the core, we snap the core off, we take it out, and now we feed it into the rover where we're going to process it. This is going to be important for the very last thing I show you. We have an anomaly associated with the stage right there. I'll show you that. So here's the sample tube being transported into the rover, and here is this exquisitely complex piece of hardware. There's an arm here. It's going to take this sample tube and put it through a series of stations where we do things like take a picture of it, we determine how much sample is in the tube, and we seal it. So there it is, telling you what we're doing here. And then we take this tube and we put it back in the kind of thing that looks like a beehive here. Each one of these is a little silo where an empty tube begins, and then we put a full tube back in it. So this beehive is ultimately going to be filled with filled tubes. Right now it's filled with empty tubes. And then we drive away. So that was the plan. And I can tell you that this capability, it is central to our mission, and it is extremely complicated. And it has taken many years for the team to develop this capability. And I tell you that because when we first tried it, it didn't work. And so here we are with that abrasion patch that I told you about with the holes in it. We reached out, and well, I'll just tell you the story how we experienced this. So we are not in communication with the rover. You know, we don't joystick the rover. We communicate with it a few times a day by communicating with an orbiter around Mars. And that means we get bursts of information back. So what we did is we instructed the rover to reach out and core this rock. And then we waited. And at about 1 o'clock in the morning on Earth, we got our first image back, but it was only part of the process. So we got this image, and we were all super excited, high-fiving. The rover has successfully drilled a hole. And so what you see is the hole that we expected, and the tailings pile around it. And then about 9 o'clock in the morning, we got more data down, and we got the signal that the tube had been processed through the rover and sealed. And we were getting ready, literally, we were getting ready for the press announcement that we have cored our first sample, when somebody looked at the image down the tube, and this is what you see. Nothing. What you are looking at is the reflective bottom surface of the tube. We got no rock. And to say there was consternation is an understatement. It was a very deflating moment. Apparently what has happened here is this rock is so friable because of the alteration that you see here, that in that step where we pulled the tube out of the ground, basically the powder that was in there must have fallen out. So we lost the sample. So this is not a good thing, but it illustrates an important point that unlike a lot of science, when you build a rover mission, you have to build capability to interact with materials that you don't understand, that you don't really know much about. So what are the characteristics of Martian rocks? Well, we have almost no data. We really don't know how to do this, and apparently in this case we were a little bit too violent with the rock. When we were percussing, we actually broke the rock apart. What do we do in that regard? Well, basically the engineers turned to the scientists and they said, we need to find a rock that is not likely to fall apart. help us find a rock that won't fall apart so we can establish whether our capability works. And so we directed the team to an area called Artubi Ridge. That failure that I just talked about happened right here. We directed them to this place called Artubi Ridge, and that's what this looks like, using the simple idea that rocks that stand up against the sandblasting. So I told you that these rocks are getting sandblasted. The rocks that survive sandblasting, well, those are going to be the hard rocks. And so we guided the team up to the top of this ridge where this is a close-up of that ridge. And these rocks are just, they look strong. And, this was I was the one that was sort of pushing that. Let's go to the top of the ridge and find the really hard rock. And then we found such a rock. This is a briefcase-sized rock on top of that ridge that we all agreed, this one looks like a rock that if you hit it with a hammer, it would go ping and it would stay together. And I was certainly hoping that would be the case because, failing twice is never a good thing. We did not fail. So we cored this rock, not just once, we cored it twice. Here you can see a little bit of how that works. Here's the drill bit with its cutting teeth. We're just spinning it so we can get a look to see whether the drill bit was damaged by boring this rock. Here's an image now. Instead of an empty sample tube, you're actually looking down a filled sample tube. And what you can see and what we were very excited about is this is almost exactly a perfect core. So that if you looked at a brand new piece of chalkboard chalk that you pulled out of the box, it would look like this on the end, a perfect circle. In fact, both of the samples that we took from this rock look like this. So we have now collected 5 cores. We attempted a 6th one, which I will show you where we are with at the end of the talk. But the basic idea here is we have now collected samples that will be very valuable for study on Earth for a number of reasons. But now I want to digress for a moment and tell you why sample return is important. Sample return is important to answer things like, what are the ages of any geologic phenomenon on the surface of Mars? And I suspect that this audience will be familiar with the way that that planetary scientists estimate the surfaces of bodies beside Earth is to count craters on it. With the idea that if you have a surface which is instantaneously created and exposed to the flux of impactors, if you know the impacting rate and how it has varied through time, you can calculate how long that surface has been there. It's a standard way to do things, and that's how we know, and I'll put that in quotation marks, that Mars dried up about 3.5 or 3.6 billion years ago. The problem is that's a model. We don't actually know the impact flux. And even worse, we know that Mars has experienced geologic processes such as erosion and deposition. So a surface, say, of the moon, which just sits there after it was produced doing nothing, that's not what happens on Mars. Mars will bury that surface and Mars will expose that surface, and that will undoubtedly yield inaccurate ages. So how do you fix that problem? You bring a sample back and you use radiometric dating methods in a lab like the one I have here at Caltech. So dating is a really important thing. As I like to say it, that's the x-axis of history. You want to have a quantitative x-axis of the geologic history. So igneous rocks are great for that. We will be able to date, when this rock come back to Earth, we will be able to date it. My guess is it is just shy of 4 billion years old. And we will be able to date it, I would expect, to a precision of probably 10 million years. So that'll be a spectacular advance. We will learn about the early geologic evolution of Mars as a planet. So when planets are born, they don't have, using Earth as an example, we didn't have continents on Earth. That is something that happened over billions of years. And so the first igneous rocks that came out of the Earth's interior were very different than the ones that come out today. So it'll be nice to see how that worked on Mars in these rocks. And then what I think is particularly interesting is these rocks have recorded a period of interaction with water. So we will learn when that water was present, we will learn what its characteristics were, and they are potentially habitable environments. They are likely subsurface environments. They're basically not on the floor of the lake. They are below that level. They are essentially groundwater, I believe. So they will be really interesting to learn about history. All of this is the kind of thing that is very hard to do with a rover. That's why we want to do sample return. So I will close with with this. How is this going to work? So the Mars 2020 mission, it has the task of filling samples in those tubes, and then by one means or another, getting them to a follow-on mission. So we are not responsible for getting them back. And this is turning out to be quite a complicated affair of how we're going to transfer them. I'll give you some ideas when I circle back through this. But right now, NASA and ESA are jointly working a set of missions to get the samples back. And they will involve transferring the samples that are presently on the rover or on the ground, and let me get back to that, into a sphere that's about the size of a soccer ball. So picture the samples stored in this container that is a sphere that is essentially the nose cone of this rocket. So we call this the Mars Ascent Vehicle. It gets launched into orbit. By the way, this is being, most of this is being developed at JPL. And this gets launched into orbit. And then in the end, the only thing that is orbiting is the ball that has the samples in it. It then gets collected by a third mission. So this is the second mission. This is the third mission. This one is right now being designed and potentially built by the Europeans, where that ball gets captured. And it always seems magical to me that you can locate and capture something the size of a soccer ball in orbit, but apparently people know how to do that. So we will capture this and it will be brought back to Earth. And right now the plan is it will be landed in the Utah desert. So if all goes according to plan, these samples will be back on Earth in the early 2030s. And I think they are going to be hugely important for the reasons that I just said in terms of what we will learn about Mars. But there's another element of this. We, the scientific community, have never had to address the question in a truly serious way of looking for life as we don't know it. And this goes to really fundamental questions like, what is life? And with the way I like to look at it, somebody's going to get handed a sample and told, you go figure out whether there's any evidence of ancient life in this rock. And it might be life as we don't know it. And that's going to really motivate people to develop new technologies, because it is, first of all, it is a grand scientific question. Is there life beyond Earth? And it will require a lot of clever thinking. So I think there'll be a lot of innovation on the boundary between biology and mineralogy, because it has to be recorded in minerals, and as well as planetary history. So a lot of interesting stuff that's going to come out of that. Let me just say one thing that is turning out to be a really interesting and complex aspect of this. NASA has not before had missions that need to be so carefully coordinated and across decades. So we started this mission in 2013. The samples might come back to Earth if all goes according to plan, in 2031 or 2032. This requires a very long time horizon, in which many of the people who designed the capabilities of this rover, they will not be on the scene at the end of it. And one of the ways that we see that is thinking about how we will do the transfer. And one way that has been considered is we will just keep the samples on the rover and we will literally drive up to the lander, and by by a transfer arm that is on the lander, we will hand the samples over. Well, that requires something special. That requires that this rover last way beyond its qualified lifetime. So qualified lifetime is basically the warranty period on the rover. Our warranty period is 2 Earth years, which will get us to 2023. This is going to land in 2029. So that sounds risky. And one way you reduce the risk is you put some of the samples down on the ground so that if Perseverance fails, there's a target. But then you have to have a rover that comes over, what we call the fetch rover, that comes over and picks up the samples and brings them back to the Mars Ascent Vehicle. So this is all a work in progress. And I think within the next year, the plan will solidify how this is actually going to happen. But it's a very interesting, a lot of wheels in motion here that are going to affect how we behave on the Mars 2020 mission and how these missions come together. So that's the plan for sample return. And then I will just conclude with this. One of the interesting things that NASA requires of rover missions is that our images, when they come down from the rover, they go straight to the internet and you all can look at them at the same time we look at them. And we got down this image. Actually, we knew there was a problem before we got this image, but when we were taking the sample into the rover, so we were mating the robotic arm to a dock on the front of the rover, we got an indication that it had jammed. And it took us about 4 days to maneuver into position to get this image, but it doesn't take a genius to figure out what has jammed this up. So what you're looking at is the port where the sample would be transferred into the rover, and it's got a rock in it. A rock fell out of the sample tube and is jamming the mechanism. And as the lead engineer of this system told me, there are not supposed to be rocks there. This is not something that they had designed to. So this happened just around Christmas, and we have been working on it ever since. We have now successfully removed these rocks. They are no longer in the way. If you look closely, though, you'll see that there are 2 other rocks down here. They are still there. And whether they pose a problem, we are not sure. These ones definitely pose a problem because we cannot get the sample transferred. They're gone. We think we can do the sample transfer. We're doing a little bit of work this weekend to try to get these rocks, out of the, out of this delicate mechanism. But I just put that out there as, boy, it's always something new. There's just always something new to be dealt with, and it's both the challenge and to some extent the fun, the stress of the whole operation. So I'll stop with that, and if y'all have time, I'm happy to answer questions.
Professor Farley, thank you very much. It's amazing, and particularly the images of the landing are absolutely stunning. I thank you very much for this. Let me ask for questions. Turn on your microphone and we'll take questions.
Well, I can start with the first one that I see in chat.
Yep.
About hard rocks versus friable rocks. That particular sample, we believe, and I'll be honest and say it is just a belief, that in hindsight, we steered ourselves to the weakest rock that was there. And it's because that was our first sample. And the engineers said they wanted a very flat surface to take the sample. Well, in hindsight, the reason it's flat is because the wind has just completely smoothed it off. And so I'm optimistic that that is the case. And so far, all the other rocks that we have attempted have not shown this behavior. And then the other question is, what kind of mitigation? It's a lot like a hammer drill that you would buy at the hardware store. It spins and it percusses, so it hammers while it goes around. And we have been making adjustments, but the trouble is, a test bed on Earth. The problem is we don't actually know what the properties are of the rock on Mars, and just because we can make it work on Earth doesn't mean we can work on Mars. But one of the interesting things is literally just yesterday, we were talking about going back to this location and trying again. And scientists are very interested in all those alteration minerals, and they would really like to get a sample of this to bring back to Earth. So possibly within the next 3 or 4 weeks, we may be back at this site, which we call Rubion, trying again. So hopefully that'll work.
Well, can I ask there must be a set of rules, a set of protocols. So when you're driving around, how do you decide where you're going to take a sample?
Well, this is maybe just the personal experience of this. I've never seen anything like this. I've spent my entire career working with a group of between 3 and 7 people. Every day we have a group of it's probably about 50 engineers and a comparable number of scientists. We begin our day looking at the data that comes down from the rover. We turn the bits into the data bits into images and real science data. We interpret it. We come up with a plan. That plan gets turned into code. And literally by the end of the day, and that day might be something like 10 hours long, we've got to have instructions beamed up to the rover. So it is very fast paced, very high stress, because nobody has time to really think. But that is the process by which we decide where we're going to go. And as an element of that, and maybe it's what you're hinting at, is the scientists are basically the ones that say, here's where we want to go. And the engineering side, the people that do the operations, are the ones that say, yes, we can go there, or yeah, no, we're not going to drive across that sand dune. We're not going to drive across that boulder, or we're not going to try to, sample that rock because it's on too steep a hill. So it's all a negotiation, and that negotiation has to happen really fast. And when I mentioned that this team had never been co-located, we have never actually sat down together and met each other. You can imagine that it's a weird human experience for all of this. And ultimately, the way it is working out is, and I'm pretty happy with this, the science side says we're really interested in trying to take a sample here, and the engineers give it their all to get us there. And sometimes we're not able to, and we just have to pick a different place.
Well, it's quite a team of people there that you've got, and scientists and engineers all working together. It's absolutely remarkable. It raises a question. You've been involved with this mission since, I think, 2013.
Right.
And you've been involved in the from the science side in the design of Perseverance. There must have been trade-offs. There must have been problems, challenges that you encountered in doing the design. What was that process like?
That is a really good question. And if you know scientists and engineers, which I bet a lot of you do, scientists and engineers, they can be equally smart and clever, but they think differently. And the way I boiled this down in my head is when developing the spacecraft, the engineers ask you as a scientist, what do you need? And they always want to know, what is the minimum that you will accept? And as I boil it down, it is to an engineer, good enough is good enough. To a scientist, good enough is never good enough. Meaning that you tell the scientist, what is the minimum you will accept? And you immediately feel like, wow, really? You're only going to give me the minimum I will accept? But that's the way you have to build something. We have a set of requirements, meaning, for example, the drill, we actually set a requirement. It must be able to drill at a certain rate through a target rock that the science side picked out. Turned out to be the Bishop Tuff, which is a rock that occurs up near Bishop in California. And so they built the thing to do exactly that. And there are other kinds of rocks that are much harder than that rock that we agreed, well, if we find a rock that's that hard, we're not going to be able to drill it. So that's the kind of trade-off that we had. But I would say in many ways, this is a very, it's a really interesting endeavor to watch how one goes about building something of this complexity and guaranteeing that it's going to work in the end. I had never seen anything like it, meaning that you start off with a few high-level objectives, some of which I showed you. And then for each one of those objectives, you write a bunch of high-level requirements, like you must have a spacecraft that can travel to Mars. And then from that requirement, there will be a bunch of other requirements that then feed down to other requirements. And it's like this giant pyramid. And at the bottom, the requirements will be, you need a bolt that has this strength. And then they build that thing. And then this is just describing the system engineering of the thing, that then after you've built all of it, you go and check, did you actually use the right bolt? And if you did, you can tick the box and you can know that the whole system was going to work. And to me, that's just a fabulous way to build a complex system when you've got hundreds or even thousands of people working on it at the same time.
The anomaly you showed was in getting the sample into the container. So how does that prevent you from driving the rover from one place to another?
Yeah, so this is actually not going into the sample tube. This is where the tube is supposed to be transferred inside the rover. So what happens here is the robotic arm docks against this port and feeds the sample tube in. And the risk of driving is that if these pebbles fall, what's down below this, and the thing that is down below it is that exquisitely complicated mechanism, and engineers absolutely do not want to have this particle wedged into an actuator, for example. So we had to move very carefully. And these ones here, they are probably not a problem. These ones, there was a known pathway where they could get into trouble. And we just got these out a couple of days ago. And what they really didn't want to do is risk driving and having them fall down through some opening and then getting where they weren't supposed to be. So that's why we didn't drive.
Ken, how did you get it out? How did the rocks get out? Did you tip it upside down or pick it out? How did that work?
Yeah. So somebody mentioned here, too bad you don't have something to blow it with. We actually do have something we could blow it with. We have compressed gas that we use to blow dust out of the abrasion patch, because you'll have the tailings in there, so we can blow that out. And that was put on the list of possible solutions to the problem, but it's very uncontrolled. And you do know the first and foremost, if you are an engineer trying to fix a problem on a spacecraft on another planet, do no harm. And so you don't want that thing to go elsewhere. I jokingly said you should pick up the rover and shake it, but they didn't like that idea either. Although ultimately what we did is the mechanism that is in the background there can rotate. And by rotating it, we managed to impart some motion to the pebble. So this thing can rotate. Actually, doesn't rotate about this axis. It rotates about an axis about right here. And we managed to motivate these particles to go through this opening over here and fall to the ground. These here, the plan is we're going to drive not very far, because we're in a good place to do this, where the rover is going to be on a little bit more of a hill, and then we're going to wiggle the wheels. And so we think we can impart some motion to them and get them to fall out as well.
Other questions? Please, anybody?
I saw an earlier question from Ben. What were the lakes, the ancient lakes, what were they made out of? I mean, it's not the Pacific Ocean. What kind of water, what kind of substance was in there?
We don't really know, but the evidence that has been obtained both so far by Perseverance and also by Curiosity, which is exploring a broadly similar environment, there's not a lot of evidence for thick salt deposits. So if you live anywhere in the southwestern US, you can see places that are filled with old lake beds that are filled with salts. We don't see any evidence for salt beds, which is strange. And it suggests that the water was not especially salty. And although it must have, in this case, in this crater, the floor of the crater is much lower than the spillover point, the channel that takes the water out. So we know that at least 100 meters of water dried down in it, and we don't see any salt bed. So we think it was relatively fresh. And the indications that come from Curiosity and also from the preliminary results from Perseverance is that this water was neutral pH and had the elements which are necessary for things to live. Like it has nitrate, it has phosphorus. So it looks like a habitable environment by every characteristic that we know about. And in our case, the most likely interpretation of this is that it was being fed by either snow or glacial melt. That's where the water came from.
I heard of.
But how do you know that the liquid was water?
I'm sorry?
But how do we know that the liquid was water?
Well, so this let me just give it some backstory here. When the first orbiter images showed channels on Mars, there was a lot of debate about it because at that time, and still today, so that was more, 15, 20 years ago, but still today, climate models cannot find a solution that allows Mars to be warm enough to have liquid water on the surface. Mars is just too far away from the sun. And there was actually years of debate as to whether the geologists were right that these were river channels cut by liquid water. And all of the characteristics that are seen are consistent with liquid water. And this includes things like the shapes of river channels. If it was cut by any other kind of liquid with a different density, the shape of the river channels and the river deposits would look different. And then ultimately, all of the rover missions that have been to Mars have seen evidence that the rocks have interacted with water. There's no other interpretation for many of the substances that you see in these rocks, like the salts that I was telling you about. That has to be desiccation of a brine, basically. So there isn't much doubt about that anymore. And from my personal point of view, one of the really great questions that I'm pretty confident will be answered when we get these samples back is how it was possible for the early Mars to have liquid water on it. The atmosphere must have been much denser than it is today. We'll get things like an indication of the temperature of that water, its salinity, that sort of thing, which should be useful to reconstruct climate. And in fact, this is the same set of techniques which have been used to reconstruct Earth's climate back, billions of years. So we're going to learn a lot about how all of that works.
Go ahead.
Oh yeah, I heard there was some like perchlorate salts on the surface of Mars. Where do they come from, or is that true? Or...
Yeah, we have found perchlorate. Curiosity found perchlorate, and previous missions have found perchlorate, and is undoubtedly there. I will be honest and say I was very skeptical, and I have my name on a paper where I expressed that skepticism, but now I have to accept that perchlorate is there. On Earth,
it's nasty stuff, actually.
It's what?
It's very nasty to life.
Well, it's so interesting. I'll get to that. But so how do we think it gets there? I think the leading contender, at least on Earth, the way you make perchlorate, which is it's a very, very oxidized form of chlorine. It is made in the stratosphere. So it involves high energy reactions of chlorine aerosols. That's how it's formed on Earth. That is likely, I think, how it is formed on Mars. But one of the really fascinating things about perchlorate, we hear about it on Earth a lot because it is used as a rocket fuel, and it has gotten into groundwater, and it is a human health hazard. It is actually it itself, the perchlorate, the ClO4 molecule, is very stable in groundwater. It doesn't react with much of anything. And that actually makes it really hard to mitigate. But once it starts to reduce, once it starts going towards less oxidized chlorine, it becomes very, very reactive. It's essentially bleach. And so one of the interesting things is in the case of these Martian rocks are billions of years old, and they still have that perchlorate in them, which means they are very stable under those conditions. And that probably means they are not particularly aggressive. And both Perseverance and Curiosity have found in rocks that have perchlorate, they've also found organic molecules. And the interesting things there is many people initially believed that the perchlorate, with its very strong oxidation capacity, would have basically oxidized the organic matter into CO2. That's obviously not happened. So it's not a very good answer, but that's what we know about the perchlorate so far.
Is there I love science
Thank you.
fiction. And is there a possible scenario where the Mars orbit was changed because of an asteroid impact or something like that? Because we're talking about billions of years. Would we have any way of knowing that?
What we know is that there are very large impact basins on Mars, including what many people believe what I call the northern lowlands right at the beginning. That is probably the result of a giant impact. But how and when those things happened, we don't know. And one thing I would point out, and this is really interesting from the geological perspective, the images that I was showing you are of landscapes that are largely unchanged for billions of years, with the exception of impacts. And that makes it very not like Earth, where, even an impact that happened 5 million years ago likely has disappeared underneath all sorts of erosion. And so there's a long record there that can be potentially sorted out, but has not been sorted out yet.
So in the famous movie, The Martian grew potatoes on Mars. With the perchlorates and with the soil chemistry of Mars, let them do that. If we send people to Mars, can they grow stuff?
Yeah, that's what I was thinking.
Well, generating food, I think, is going to be the least of their problems when they're on Mars. So I'm in this audience, I'm going to be totally honest. I often get asked to describe how humans are going to, solve all our problems on Mars. And I think the biggest challenge is going to be to keep humans alive on Mars. And what from my sort of armchair watching this mission is a very expensive mission. At the end of the day, this is about a $2.5 billion project, just Perseverance. And we did speak openly that when we landed, we accepted about a 7% probability of failure, meaning we would land on a rock. This wasn't a guess. We actually knew where there were rocks, and we estimated, what the likelihood of failure was. So you can do that if you're just a robotic mission, but if you have humans on board, you can't do that. And as the engineers explained to me, for each 9 in the 99 to 99.9 to 99.999% probability of success, it's another factor of 10 in cost. So what concerns me about sending the humans there is we can't afford it. I don't know where the money is ever going to come from. This is probably $100 billion proposition to do that, and that's just a crazy amount of money. I'm not speaking for NASA. I'm speaking for myself.
Is there also a problem that when people talk about going to Mars, they talk about, we can do it in a 2-year mission, and yet when you figure out the orbital mechanics, I'm not a great mathematician by any means, that we're really talking about a 6 or 7 or a decade-long mission to reliably go to Mars when we want to.
Yeah, I'm not an expert on that either, but what I have been told is if you build a big enough rocket, you can go pretty much anytime. And so it just depends on how much you want to invest in your rocket. So I mentioned this 2-year, 26-month, best case. That is for a relatively inexpensive rocket, but like the big new, I'm going to forget the name of it. The big rocket that NASA is building right now, that actually you could use that and cut the time and go whenever you want, but you pay a lot more for it.
It always boils down to money. How many $1 trillion do you want to spend? If you want to spend it, you can do it.
Yeah, I think that's right.
Well, can I follow up on that, on Tim's point there? Suppose, looking ahead, suppose you had a large pot of money that you could allocate to science projects as you wish, billion here, billion there. How would you allocate that money? Would you spend more money on Mars? Would you look toward other locations in the solar system, or are there important projects in terrestrial geology and geochemistry that you think really are important and need funding?
Yeah. Okay. So that is a polite way of getting the question that I sometimes get from more hostile audiences is how can you justify spending so much on this? And I say I don't have to justify it because I'm not the one who made the decision.
Yeah.
But look, I mean, let's be honest. This cannot be this effort to do a lot of the things that we do at the NASA scale is not justified just on the basis of the science that you get out of it. I know what $2.5 billion invested in some kind of geoscience, that would be gigantic. It's probably more than over an equivalent time period actually gets spent on doing that. So there's a disconnect there, which tells me this is not primarily about doing science. It's about other things. And what are those other things? And definitely there is an increasing space race. Nobody really wants to talk about it, but it doesn't, you just look at the situation and the Chinese have landed a rover on Mars. They are talking about sample return. I think the US wishes to maintain that lead that we've had for so long. So we are pushing forward with bringing these samples back. But the one that I actually resonate with more is there are a small number of really enormous projects that get done by the US and by other countries. James Webb is one. This is one, the whole sample return campaign. And I'm actually good with putting that in the perspective. Yes, this is a lot of money, but it is a small amount of money compared to the entire range of things that, for example, our federal government supports. And honestly, this one should make us all feel good. And when there was in a longer version of the video that I showed of the landing, there is a moment right at the end when President Biden, who called us the day after we landed, he made a comment that we were exactly what America needed to get out of the pandemic blues, that we still managed to do great things. And so just speaking personally, I look at a lot of the big things that are happening in the world and they do not make me feel good. But I feel good that we are doing something now that is uniquely human. It is exploring and it is exciting to people and it encourages people to go into math and science and engineering. So I think it serves a lot of additional purposes. I won't try to, direct the money. Obviously, climate change is a huge issue. I'm not sure we need more money to understand that climate is changing, but maybe it's time to worry about mitigation. I don't know.
How do you attract graduate students to work on a project whose timescale is decades from conception to analysis? A graduate student has a timescale maybe of 5 years. They don't want to work on something that's going to take 25 years.
Job
Right.
security, come on. Grad student.
So I did not have any graduate students working until we arrived on Mars and are actually doing science. And there's anybody who started before that, for example, working on the, say, calibration of the science instruments, they did it on risk. That we would either not land successfully or the budget would be cut before, every year there's a review during the development cycle, like, do we go forward? Do we go forward? And, sometimes missions get canceled. So my solution was just to not put a student into that situation.
But I'd like to suggest a point. When the internet happened and I was involved in JPEG and all that kind of stuff, MPEG, none of us actually did it. We all knew that whatever we did wouldn't even show up for years and years and decades. And yet we were still inspired to build something called infrastructure, to build the basic things. And that was actually really exciting for us. So to answer your question, Mike, I think there are always people that want to do the greater good and are willing to do it now for the future.
On that optimistic note, Professor Farley, that wonderful presentation, and you've been very generous with your time today. We're an hour and a half into this, and I don't want to unnecessarily make demands upon your time. We thank you very much.
Yeah, thanks for having me.
Let me bring the meeting to a close. To close the meeting off, let me mention our next meeting. The Greenway Talks online will continue on Saturday, February 5th, when Professor Joss Bland Hawthorne will tell us why our solar system owes its existence to the Sagittarius dwarf galaxy and a collision that occurred 15 billion years ago between it and the Milky Way. In a talk titled Giant Waves Crossing the Milky Way, Professor Bland Hawthorne will describe how precision astronomy is now being combined with equally precise measurements of radial velocity to provide unique insights into how our galaxy has evolved over billions of years. Joss Bland Hawthorne is director of the Sydney Institute of Astronomy and an Art Laureate Professor of Physics in the School of Physics at the University of Sydney. I should note that at this meeting on February 5th, we will begin at 2 p.m. in the afternoon in order to accommodate Professor Bland Hawthorne's schedule in Australia. So that's in 2 weeks. And with that, again, thank you to Professor Ken Farley, and my thanks to everybody who came, who attended this meeting, who participated, who asked questions. I thank you all very much. And with that, well, stay safe, and I'll close the meeting. We'll see you again in 2 weeks on February 5th. Thank you very much, everybody.
Thank
Bye-bye.
you.
Thank you. Excellent.
Yeah.